So in this chapter, we will talk about gases. And it turns out gases is among the three states of matter we know is the most understood state. In the previous lectures, we already talked about the differences between gases, liquids, and solids, right? So can you remember how a gas is different from a solid or a liquid? One of the first things we can talk about is that a gas has no definite shape or volume. It takes on the shape and the volume of whatever container it is in. If I put a gas in a balloon, it would have the shape and the volume of that balloon. If I put a gas in a room, it would have the shape and the volume of that room, right? So it has no definition of shape or volume. And remember, we also know that the particles in a gas are very far apart from each other. And because they are very apart from each other, there's a lot of space in between. We also have learned that they are not very dense. And because they are not very dense, they are very easily compressible. So these are the things we know about the state of gases, how they are different from solids and liquids. And because gases is one of those states that tend to be invisible, we often don't think about them as much, even though they surround us all the time. For example, around us, we have gases like oxygen gas, nitrogen gas, or hydrogen gas, right? Or even carbon dioxide gas. So even though we don't see it, gases is one of the states of matter that is most well understood, and we can understand it using a model for us called the kinetic molecular theory. And in this theory, there are 5 principles that help us understand the property and behavior of a gas. The first is that gas consists of small particles that move randomly with high velocity. So the key in this one is that they move randomly and high velocity. So imagine if you open a perfume bottle, what do you notice? Right? In a few seconds, that perfume, the odor of that perfume spreads throughout the entire room. It happens very quickly, and it doesn't go in one direction, right? It goes in all directions in that room. And second, they have essentially no attractive forces. So because gases don't have attractive forces, they don't stick together. And because they don't stick together, they get to spread out and be all over the container that they are held in. Third, the gas molecules have very small volumes compared to the volume of the container they occupied. The volume of the container they occupied we call the volume of the gas, right? So again, this states that the volume of the molecule is very small compared to the volume of the gas itself. That means that the gas volume is basically empty space. Because it is mostly empty space, you can actually then compress and push the gas molecules closer together and making it more dense. So that's why gases can be very compressible. Number 4, they bounce around constantly in straight lines. And as they do this, they are bouncing and hitting the wall and exerting a pressure on the wall of the container that they are held in. Number 5, they have kinetic energies that increase with increase in temperature. So the more temperature you have, or the more temperature you give to a gas, the faster it moves. It is directly related to one another. Okay, so when you are asked to describe why a gas behaves the way it does using kinetic molecular theory, you want to go back to these 5 principles to explain how gas behaves. Now let's talk about how we can measure the quantities of a gas. We call those the properties of a gas. There are 4 of them. The first we want to talk about is volume. Right? The volume is, as we have said before, is the size of the container. The volume of a gas in a basketball is the size of that basketball. The volume of a gas in a room is the size of that room. So we usually measure volume in units of liters or milliliters. Next, a property we can also measure is the temperature of a gas. So take a look at this example here is a hot air balloon. In the atmosphere, you can measure the temperature of that day. It's quite different, whereas the temperature inside that balloon, the temperature inside the balloon is hotter than it is outside. So there you can measure the temperature of those 2 gases. As we said previously, it's proportional to the kinetic energy. And often the unit we will use is kelvins to do calculations. So be aware that you have to always convert everything to kelvins when you do calculations in this chapter. Even though we see that gases can be measured in terms of Celsius or in Fahrenheit, but just convert it back into Kelvin before you do any calculation. Next is pressure, and pressure is one of the harder ones to understand in the four properties of a gas. The definition of a pressure is the force over an area. Okay, so pressure is directly related to force, but inversely related to area. What does that mean? Directly related, that means if force increases, pressure will increase. If force decreases, pressure will decrease. That's what directly related to means. What does inversely related mean? So area is inversely related to pressure. That means if area increase, pressure would decrease, right? If area decrease, pressure would increase. That's how inverse relationship works. So an analogy to this I like to give is that the amount of work you might receive, right? Let's say in one day your boss gives you amount of work and you feel like that amount of work you can handle, so you're not very stressed out. So your pressure is low, right? So how would you able to increase the stress or increase the pressure? Well, you can increase stress you have if your boss gives you 10 times the amount of work just to you. If you have more work, you have more stress, more pressure. Right? The same thing here. If I increase the amount of force, I will have increased pressure. So what if I ask you, how do I decrease the amount of stress? Let's say that your boss did give you that 10 times the amount of work. How would you then decrease it without decreasing the amount of work that the boss gives? Well, one way is you distribute that work out, right? So instead of you working, maybe you bring in 9 other people to work. So therefore, that 10 times amount of work is distributed among 10 people. So then your stress that you receive now is decreased because you basically have the same amount of work now. Same thing here. If you have higher force, but if you want to decrease the pressure, you can increase the amount of area distributing that force all around. So when we talk about pressure and force and area is because that the pressure we talk about here in terms of gas pressure is the force exerted by the gas particles. So we want to know what force is exerted and what area we're talking about. The area here most likely is going to be the container where the gas is held in. The unit pressure is also very funky. There's 3 that I want to highlight here. The first one is ATM, which stands for atmospheres. And the second one is mmHg, which stands for millimeters of mercury. Very funky, right? You should notice then that millimeters is a unit of what? Height. So we'll come back to that. Why is there a unit of length, I mean? Why is there a unit of length related to pressure? The third unit is torr, and the last unit here is psi, which is a non-SI unit. Is an English system unit. It stands for pounds per square inches. All right, so again, we'll come back to pressure because that's a little bit harder to understand, so we'll extrapolate a little bit more. But you know that we can measure pressure and different areas have different pressure. For example, the sea level, you have a pressure of 1 atmosphere, whereas when you go up the mountain, it has less pressure because there are less molecules bouncing around up there, so there's less force on you as the molecules are bouncing, so the pressure is actually less in the mountains. In this case, is noted in the mountain, the pressure is 0.70 atmospheres. That's also one of the reasons why when you go to places like Colorado or very high mountains, if you're anemic or anything, you might have a harder time breathing because there's less oxygen, basically, up in the mountains. All right, the last quantity I want to talk about is the moles. So one way we can describe a gas is the amount of gas that you have. So that is in terms of moles. And of course, the unit for moles is mole, but you can also see it in terms of grams. If you know the molar mass of a gas particle, you can convert grams back into the moles. All right, so those are the 4 quantities. And as promised, we'll go back and take a closer look at pressure of a gas. So particularly, why is pressure of a gas measured in millimeters of mercury? So it turns out one of the first people who studied the pressure in the atmosphere, his name was Evangelista Torricelli. What he did was he took a glass column filled it with liquid mercury and inverted it into a dish that also had liquid mercury in it. Now, you would imagine that this would just kind of flow all out and empty itself out onto this dish, but it actually doesn't because of the atmospheric pressure. What that means is that there's always going to be gas particles around here. And remember, gas particles are bouncing and bouncing, and they do exert a force, and they do bounce onto the top of this liquid here, and they exert a certain amount of force, so it pushes the liquid back up into this column. Now, if you have high amount of force, high atmosphere, high pressure, you would push this column higher. And you have low amount of pressure, it would have less amount of force, so it would push it lower. And then you can measure how high that is pushed using a ruler, measure it in millimeters. So it just turns out that at 1 atmosphere or at sea level, the column of liquid mercury rises to 760 millimeters of mercury. So that's how we get that unit. So if we were to take this column and put it up into the top of the mountain, you would see that this number would decrease, right? That's how we got millimeters of mercury, but that unit now has been replaced, but we still use it sometimes, but it's been replaced in the SI system. We now replace that as torr for the inventor of this apparatus. And 1 millimeters of mercury is equal to 1 torr. Okay, so let's now have a checkpoint to see if you can describe the properties of a gas and how they behave. Explain this phenomenon. And also think about if you ever noticed this before. When you take a potato chip bag up the mountains, the bag puffs up. Why do you think they puff up? So the answer is B. At higher elevation, the pressure inside the bag is greater than the pressure outside. Right? So if that potato bag of chip was manufactured at sea level, it has the atmosphere of the sea level, which is higher than the mountain, right? So when it goes up the mountain, the pressure inside the bag is higher than the pressure outside the bag. Because the pressure inside the bag is higher, it is better at pushing out, and the pressure outside the molecules is less able to push in, so then therefore this potato chip bag would then puff out like this. Another example of this reminds me of when I went to Sequoia National Forest, and I noticed this happens to a bottle of mine. So what happens is that when I was using this bottle up in the mountain, I capped it, so the inside of that bottle has the same atmosphere as the mountain's atmosphere, which was 7,000 feet above sea level, meaning that it's less pressure, right? So when I drove back down to Los Angeles, where I live, which is 200 feet above sea level, so it would be higher pressure on the outside. This is what happened. The pressure outside is higher than the pressure inside. You can try this next time you go up the mountain, or when you fly in a airplane. Try to open up a bottle while you're in the air in a very high elevation, close it, and then once you get down back at sea level, see how that bottle has changed.